GPU computing with Go by Arne from Ghent University.
Hello everyone. So tomorrow there's actually a player dev room about Go being used for all kinds of web services and so on. This is something completely different. We're using Go here for a purpose that was not intentionally intended to. So I mainly want to give you some feeling how well is Go suited, what are the pros and cons with Go for scientific computing. I'm sharing this from my own experience at Ghent University, where I have been developing a so-called micromagnetic simulation program that can be used to model, for instance, hard disks, magnetic ramps, and so on. Since this is the scientific HPC session, I'm allowed to show at least a little bit of science. So just to give you an idea, this is the partial differential equation that we have to solve for many, many millions of discretization cells and many, many millions of time steps. And it covers all the different sides all with each other, so it's pretty computationally intensive. So that's number crunching part we mainly offload to the GPU. But there's lots of other code than just that. So typically the bottleneck is only 10% of your code and you still have 90% of your code left. You have other stuff. And that we decided to try to write in Go just for fun. So our implementation for this problem with CUDA and Go was only around 11,000 lines. And if you compare it to some other programs that do basically the same thing, they use some C++ together with a scripting language, and they require like really a multitude of these lines of code. So yeah, it's been really a good choice in terms of productivity, but that doesn't necessarily mean that Go is like a complete smooth ride for computational HPC. So what are the strengths and the weaknesses here? So I will show this in 3 scenarios. What if you're doing pure Go number crunching? What if you're calling some external library, C, C++, or maybe CUDA? And finally, what if you need concurrency in your program? Maybe I should introduce a little bit Go for the people who might not know it. So it's a compiled statically typed language. So basically you expect it to be quite fast, but at the same time you get garbage collection, memory safety, some dynamic features. Yeah, so it's somewhere in between scripting and say C++. Typically programming language is introduced by some Hello World program. I'm going to show a Hello Math program. This is some actual Go code that calls some things in the standard math library. I'm going to compile it and run it in my browser. That actually worked. So it showcases a few of the nice features of Go if you want to do some mathematical stuff, some number crunching. It has precise compile time pulses, so this expression is not truncated to 0, it's handled precisely. There's complex numbers right into the standard library, that's handy. Even special functions like these basics are just in the standard library, very handy. And there's even out-of-the-box support for large arbitrary precision numbers, like this very large binomial expansion here that you can get just out of the standard library. So that's pretty nice. However, some sorely missing features are most notably matrices and matrix libraries. These you do not get out of the box, you don't have to get them elsewhere. Okay, having some math is a nice thing, but how about performance, of course? This is a high performance session, so how well does Go perform? Let me show a simple dot product example. This is Go code to make the dot product of these 2 vectors just the sum of the product of elements. And you can very easily benchmark this with Go's built-in testing and benchmarking framework. So you have to write some benchmark dot function. It has to start with benchmark. That just sets up inputs and calls the function a number of times. And then we execute command go test minus bench, and it will like scan through our source, look for all the functions called benchmark something, and it will properly time them in a statistically meaningful manner. So we have to wait a little bit. And it called our function 100,000 times to get an average runtime of some 2 microseconds per operation. Okay, so it's nice to have this benchmarking built right into your toolchain. There's also unit testing in this way, so that's handy. There's also profiling built in. So you can just out of the box get a call graph from your program at runtime and it shows how much time is being spent in every function, and it makes some bigger blocks like to highlight, like here you are wasting some time, spending some time, so you can focus your optimization efforts over there. Okay, that's all nice to have, but how about really bare performance? So we go back to the dot product example, and I've compared it to the exact same code in some other languages. So this is a native Go compiler. It also has GCC support, and you see that it's actually pretty close to portable C code, so that's quite nice. Typically, not only here, but like in general, you will sacrifice around some ballpark 10% performance, for which you get in return array bound checking, garbage collection, and so on. However, it can still be several times slower than really machine-tuned C code. So that's a trade-off you make. So though it's fast enough for everyday use, it's probably not a good idea to write an extra pack or so in Go. So we'll just take that from elsewhere. Okay, so number crunching in pure Go is quite okay because there's a lot of built-in stuff. The managed memory really cannot be overstated, but we'll have to get our really high performance libraries maybe elsewhere. So that's the second part. How about calling some external library from Go, whether it's standard C stuff or CUDA to offload your number crunching to the GPU. So we can do that. It's not that hard in Go. You need to have some special comments to include your C headers and even your linker flags. You put right in the source code, so there's no special build system. You build your code just like you always do. And this is an example where I'm calling a CUDA library to ask for the name of my GPU. Let's go Linux. So this has now called NVIDIA's CUDA driver to ask my GPU name. So okay, this works, but it's a bit unwieldy. I don't like to write this all the time, and there's also conversions to and from C types and Go types all the time. So what you really want is an idiomatic Go library if you're going to do these things. So I've written one for CUDA, and you can find them for other libraries and maybe write them yourself. And Go makes it actually quite easy to import third-party libraries. So you import something by URL. So if anyone's interested, you can find the source code here. And you install it on your system with Go get that kind of URL, and that's it. So this code does really the same thing, but now it's an idiomatic Go program. And one nice thing is also that these dependencies, these extra libraries, do not have to be deployed to your cluster system. So they are always compiled in. You don't generate additional dependencies. Go binaries are typically statically linked, so it's really easy to deploy. Okay. So being able to call C is one thing, but we also share memory between Go and C. So won't that be a problem because Go is garbage collected and C is not? So fortunately, you don't need to worry about it. Go is aware of C's memory space, yes, so it will never accidentally garbage collect something that was mallocked by C. And it even gets better because the memory that's allocated by Go is always very nicely aligned. So you can pass it on to libraries that use SSD instructions or AVX, it doesn't matter. Basically, you will allocate a Go, have C-crunch your numbers, and you don't need to worry about freeing any memory. So that's a nice productivity boost. Memory management is just taken out of your hands. All right, so to wrap this up, when you're calling external C programs, external C libs from Go, there's a downside that you have to write some C wrappers or find them. Hopefully they are available. But on the upside, you can call C, and you get a huge productivity boost because you can have Go manage your C memory. All right. This brings me already to the final section. That's concurrency. Yeah, so concurrency means that your program is doing several things at the same time, not necessarily in parallel, but really different tasks at the same time. If you go back to our real-world example, our micromagnetic simulation code, some of the things we want to do concurrently with our computations, for instance, I/O. We don't want to interrupt the GPU calculations just to save some data to the disk. It has to be parallel. And also we have an interactive GUI that runs in a web browser. And yeah, this GUI has to remain responsive even though there's a CPU thread taking 100% of the cycles to keep the GPU humming. So yeah, obviously you can do multi-threading and concurrency in any programming language, but Go makes it really easy to do that by building in concurrency primitives right into the language. So for instance, for our disk I/O, so we have one thread that's always fully spinning to keep the GPU busy. And then we can spawn a lot of worker threads that do some expensive conversion of the data and flush it to disk. And with Go, it's really easy to share the data between those threads with a so-called channel. And so that's really a Go idiom. Go channel is a bit like a Unix pipe, actually. So you put data in from one side and data comes out on the other side. And it has some nice arrow syntax to put data in and out of the pipe. And this is basically the code you need to do asynchronous I/O. So in your main function, we're going to start a worker function, run I/O in this case, which will just loop forever. This is an infinite loop. And just forever it will take data from this pipe and do some expensive save operation on it. And we start this function in the background, so in a separate thread. This row keyword is like an ampersand in Bash, just rather than a different thread. And then we put data in this pipe that comes out here, and it's handled. So we have just in a few lines of code really nice concurrency. So in our real simulation program, it's just a handful of lines, and they speeded up the I/O sometimes by a factor of 2. So these are the kinds of things you can expect. You do basically the same stuff. You can also do in other languages, but there you would need hands full of mutexes and callbacks and so on to implement maybe something simple as this. Now, if this was the only use of channels, okay, it would be of quite limited use, but it becomes extremely powerful when you combine it with Go's select statement. And this is a bit like a switch, which has cases and maybe default, but it switches over channels. And what the select does, it checks if there's something available in the channel. It will take the value from the channel and execute whatever code is here. And if there's nothing available, it does some default calculation. And this is something that is very useful, for instance, for this interactive web interface. So I will show you in a minute. The user can click on buttons and change variable values while the simulation is still running. It's not pausing for that. So you have always the risk of concurrently modifying, like you modify a variable while it's being read. So typically you would have mutexes and state looking and so on. So here it's not necessary. We're always doing calculations. When our web server wants to change a value because we pushed the button, it puts here in the pipe a function. So Go has full closures. You can just have functions as values, send them through pipes and so on. So the web server sends a function with the work we have to do. It comes out on the other end in our main loop. And then we wait, so after the calculation has been done, then it's a good time to execute that function, just a little piece of code, but then we are sure that we are setting this variable when we are not actually using it. So that's a very simple way to avoid hundreds of mutexes. So one of these codes that I showed has really lots and lots of locking, and if you forget to lock and unlock one of these variables, then you get race conditions, and your code may fail, but you will never know because you have the wrong result and so on. So that's the final design we have. And one note, if you somehow still manage to get race conditions anyway, if you manage to mess it up, even though the nice concurrency primitives are there, Go has also built in race testing. So you just build your code like this, and if you manage to do simultaneous read and write of a variable, you'll get a nice report telling you you messed things up. Okay, I have a little bit of time. So if you need concurrency and Go, it's extremely it's an extremely pleasant experience in my opinion, which I really have not encountered any downsides yet. So just to give you an idea of what you can do with only 11,000 lines of Go compared to maybe 100,000 lines of C++. In other cases, I will show a little demonstration. So I have written some input scripts. Yeah, that doesn't matter. So it's this was an input script that simulates a spinning hard drive, and I will execute it right now. So that works. Okay, there we go. And so now this could be running remotely on some cluster, but if I want to, I can open my browser, connect to the nodes where it's running on, and I get this interface showing me the status of my simulation, how well it's doing. This completely does not slow down the simulation, so I've really tested it. It's running completely concurrently. The GPU does not stop its work just for serving the tool. And in this case, we are simulating a spinning hard disk platter. So here we are looking at a small piece from a hard disk platter. This is a few micrometers large, and we are looking at really at a nanometer length scale. Here there is some write head that produces a magnetic field, which is writing bits on our hard disk. So white means the magnetization of the platter points up, black means it points down, and then here the alternating field is writing a series of bits which are moving at around 7,200 RPM. And there's live plotting of what's going on, and I can change some parameters here live. So this is updated right away without any risk of race conditions and so on. So that's just 10,000 lines or 11,000 lines of code, a factor of 10 less of what similar implementation. So that's what you can expect basically from code for applications. Thank you.
Right, thank you, Adner. Let's take 2 questions. Yeah. So, how did you do your matrix calculations?
Yes, so using CUDA. So there are lots of we uploaded it to CUDA, which has matrix libraries on board, and then a few things that had to be handwritten in CUDA. So were handwritten and then wrapped. So you can call C. So you write basically some C function and you call it from Go. And I also to simplify this, so let me maybe show an extra slide for this at some time. So, so basically, if you
write your own matrix stuff, and in CUDA you need to write some kernel, then typically you would write a wrapper for that kernel, which is also C code, and then you would have to write a Go wrapper for that C wrapper. So that works, but it's a bit annoying. So I also wrote a little utility CUDA to Go that just does this task for you. So it reads your CUDA kernel and it immediately outputs a pure Go file with a nice wrapper in it, and CUDA kernel is included in the Go source as PTX assembly. So you do not introduce any additional dependencies in this way. So this Go file can even be compiled without the need for NVIDIA's compiler anymore. So you can really easily deploy it to people who want to compile it for their system, and they don't even need NVCs. So that's
have you also written support for sparse indices?
No. So this is just this wraps any kernel you do, but I have some stencil operations and so on, but I don't need any sparse stuff. So sorry for that. Maybe someone else has. If they do, then you can just wrap it in this React code from Go.
One more question?
Yeah, one of these.
Yeah, thanks. Yeah, I wanted to buy this one. But I sold it. Thank you so much.
Any more
A real question.
No? Okay. Thank you.